Hello everybody and welcome to another lecture on computer architecture. Today I want to talk to you about the timing of circuits, more specifically about hazard, so-called glitches, things that can go wrong in your circuit when it's not well designed. So let's get started. First of all, we have to introduce some definitions, some concepts. So we have here the steady state. Steady state is that output value that you have at the end when the circuit has settled and reached a stable value. So you can imagine that you wait an infinite amount of time and then it reaches your desired logic value that you have programmed from the beginning in your logic design. Now the transient behavior is that you go from one state to another, but in between you can have undesired non-programmed values. And a glitch is that value that you didn't take into account, that doesn't belong to your initial state and it doesn't belong to your steady state in the final steady state, but you get an intermediate state that is undesired. And a hazard is if your circuit has the possibility of such a glitch. Now, having said that, we're going to take a look at the so-called static one hazard. A static one hazard is when you have designed your circuit with the sum of products approach, as you all know, then of course you have an initial value based on your initial input values, let's call them X, and your final value of your output based on the final input values, let's call them Y. And the static one hazard is that these two inputs, X and Y, they differ by only one of the input variables. So one of them is different in these two sets, and both of them produce a logic 1. So your initial state is 1 and your final steady state is also 1. But in between you have temporarily, you may have a 0 in your circuit. So you may have a 0 glitch, and this is what we call a static one hazard. So it goes from state 1 to state 1. But in between you can have temporarily a 0 state, and that comes out of nowhere. Now the same thing you can also do with a product of sum approach, which then has a static 0 hazard, as you will see. Well, that is to say, I will today only talk about the static 1 hazard in sum of products circuits. I will not talk about the other one. But the same thing you can have with the products of sum implementation of your logic circuit. And then it also can have a static one hazard. That is to say, it can have static one hazard, meaning it can have static one glitches, static 0 glitches. Okay, so now let's take a classical example. First we have to find out that what is this thing based on? Well, it is actually, I have here a sum of products circuit that I already put, I will show you in a moment. But the thing is that if we have this first layer, this is in the sum of products, that is the layer of the products. So we have here two AND gates, those are the products. And because these two products can produce the result at a different time, so A here in this case, A and B are not switching at the same moment, it can be that this causes a glitch, as you will see. Now this is what is a classic example that implements with our techniques that we've learned with sum of products, and then with Carnot maps we reach this conclusion, we reach this circuit. But let's see, we have here, let's start from the beginning again. We have here this the truth table. We have three inputs, X, Y and Z, and we have an output that is given by this truth table, so it has 4 ones. What do? We create a sum of products. If you don't know what this means, then just go back to that to the lectures of sum of products and products of sums. But in this case we come up with a sum of products that is summing, that is this OR gate that we have here, that's summing a set of products that is produced at this layer. But then we did what we did with the Carnot map that is shown here. We can simplify the circuit. We join here these ones that are shown here. We join here these ones, and we come up with that it is just a sum of two products. This is product 1 implemented by this AND circuit, by this AND gate A, and this loop here is implemented by AND gate B, and then we are summing them, the outputs of these two AND gates, by this OR gate. Now also note here, and this is important, there is in front of the second AND gate there is an inverter, and the problem with this inverter is that it will create a small delay, because these are two transistors and transistors are not infinitely fast, so they cause a small delay, meaning that there can be a certain moment that we have here, this one, this Y that we have on this side can be different than this not Y that's on that side. That is to say, they can be the same. So if I switch Y, from, let's say, from 1 to 0, I go from here from 1 to 0, this one of course on this side will go from 0 to 1. But this happens slightly later than the inputs switching from 1 to 0. I've shown this here in this time diagram. So Y, it's shown here, is switching, and then not Y is just a fraction, maybe some picoseconds it's later. So we can have a situation that we're getting a 0 here and also a 0 there. So meaning that not Y is not equal, is equal to Y. Now why does this cause problems? Let's start. We have here 1, 1, 1, and for 1, 1, 1, that is this input values, and of course that will cause a 1 at the output, so we get the 1 here at the output. Actually what we have here, 1 and 1, we have a 1 here, and we have 1 and 0, that is a 0 here, so we have this initial state, and let me change the color here, let's put blue. And now we want to go to the final state. We just only switch Y, so we have here 1, 0, 1, and this one goes to 1, meaning this gate goes to 1, and this gate is 0 and 1 goes to 0, and the output is also 1. As you see, the thing is that gate A as well as gate B, they are switching. This one switches from 1 to 0 and this from 1 to 0. Now there can be a moment that gate B is already 0, gate A is already 0 and gate B is not yet 1, meaning we have this state that we get a 0 at the output. Let me put it again, then let me show you what is going on. So this one goes to 0, this one is still 0 for the moment, short time, and then you have here 1 and 0, this one is still 0, and this one 0 and 1, that one is also 0, and then at the output we get 0. So somehow out of nowhere we got a 0. That was not the initial state nor the final steady state. To put it in a diagram, you can see here Y, not Y is a little bit later, A switches immediately because it gets these two inputs X and Y directly, but B switches just a fraction later and goes to 1 a little bit later. So we go at the output, we go from 1, temporarily we go to 0, and then we go to 1. And this is what we call a static 1, because we have 1 here, 1 initial, 1 final, a static 1 glitch, that it's temporarily, it is 0, that seems to be coming out of nowhere. Now if we look at the Carnot map, we see that it occurs when both AND gates, both products are switching, and that is because we go from one loop to the other loop. So we were in here in 1, 1, 1, 1. We were going from this loop, we were going to that loop being 1. That is right. Let me see if I'm saying this right. No, we were here 1, 1, 1. That is this loop. That is xy. Xy is 1. We were going from that loop. We were going to that loop. This one giving 1 and this one giving 0. And now we're going to this loop is 0 and this loop is is 1. So because we changed the loop, temporarily we can have that they are both 0. So we can recognize this in our Carnot map, that if we have two loops that are sort of not overlapping, then we can be in trouble. We have a hazard. It doesn't mean that we get a glitch, but we might get a glitch, and that means we get a hazard. So if we know the problem, we can also know the solution. What we're going to do is simply, let me put here another color, we just simply add here a third loop. We just add here a third AND gate. So to show you this in the truth table, what do we have actually? We call this the physical truth table, that we can have X, Y, and Z. Maybe I should put this a little bit down like this and still have this one above here. We have this physical truth table because we have here X, Y, not Y, and Z at the inputs of the AND gates. So we have actually 4 input values, X, Y, Z, and not Y. And Y and not Y, they can be the same in some cases. So what do we have? We go from the initial state, which is X is 1, Y is 1, Z is 1, and not Y is 0. That is our initial state. We go to the final state with X 1, Y 0, not Y 1, and Z 1. And that also produces, the final state is also 1. But in between we can have a state, and that is given, let me put it in red, this is given by this state, that X is 1, Y is 0, not Y is also 0, and Z is 1. And this output, as you can see from this circuit here, that output will produce a 0. And that is our 0 glitch. And because that can happen, we have a static 1, 0 hazard. We go from this state to this state to this state in our, what I call the physical truth table, which is not exactly always equal to the logic truth table. So the solution then is, as I told you, is adding another loop to our sum of products. So I've added here, oh, I don't have here, I cannot indicate this. I have here added another loop, another AND gate to implement this loop here, which is called XZ. As you can see in this Carnot map, that's XZ. And now if we go from this state here to this state here, it means that we don't get a 0 temporarily. Because let me show you again. Now we have this one. It's becoming a little bit messy maybe. Let me put this one on top above my head. Because we have now, we take A, B or C, we have a sum of 3 AND gates, and in these 3 AND gates this effect of this glitch doesn't happen anymore, as you can see. We started with here with this initial state, that is X equals 1, Y equals 1, Z equals 1, and no, sorry, this is not the one. It's getting a little bit confusing. We go from this state, X equals 1, Y equals 1, Z equals 1, and Y not equals 0, and we go to this final state. That also gives a 1, and the initial state also gave a 1 here, and we go to the state that Y has inverted and then not Y also has inverted. But in between we have this state where not Y and Y are equal. But as you can see from this circuit, in this case the maintenance of the output 1 is guaranteed by this C loop. It's sort of like a safeguard. This C loop is outputting constantly outputting 1, and it never goes actually, the entire output never goes to 0, because the C loop is a safeguard. This one with 1, I don't have to here, I cannot indicate, but with X1, Y1 and Z1, then if Y changes, this doesn't affect the C loop. And the C loop was already guaranteeing a 1 at the output. You have here the C loop. This one has here 1 for Z and 1 for X. And because it is 1, 1 here, in the initial state, in the final state, and in the intermediate state, this always stays 1, 1. The output of C always stays 1, and therefore the output here always stays 1. So by joining these two loops, we can avoid a static 1 glitch. Just look again, back again, how this works. And I want to point out to you that even if we don't have this this inverter at input, but we have, for instance, that these AND gates, they are slightly different just because they are made from different transistors somehow, or from a different side of our IC. Then maybe they are slightly different, and therefore they can also switch at slightly different times. And of course, this is exactly the same problem as this inverter causing a delay. This delay can also be caused by B being slower than A. And of course, this solution that removes the problem with ICs, with the delay caused by an inverter, it will also eliminate problems of different AND gates. It will also solve the problem of hazards of having different AND gates, slower and faster AND gates. This you will just have to think yourself how that can be true, but I think that is quite logical. So we have here this solution, and then I want to mention one more thing which I didn't find in other textbooks, is that there are no static 0, 1 glitches. So a circuit like this, or actually the original, let me go back to the original. Where do I have the original? No, that wasn't it. It was this one, the original. This circuit does not have a problem with the static 0. So if the output is 0 in the initial state, the output is 0 in the final state, there cannot be temporarily a 1. And that is because an AND gate like this can switch only once. It's not that it can switch to 1 and then back to 0. And once one of these AND gates here have switched to 1, it doesn't matter that another one then also switches to 1 or switches to 0. Once one of them is 1, of course the output stays 1 and stays 1 forever. So it cannot be that it goes to 1 and then back to 0. So you cannot have a static 0, 1 glitch. That is impossible. Because each AND gate can only change a single time and cannot go from 0 to 1 to 0, because it would be 2 switches, and that is never going to happen. And once it has gone to 1, the output of the final output of the total circuit is 1, and it will never go back to 0, whatever all the other AND gates might be doing. So you only have a static 1, 0 glitch. So you only have a static 1, 0 hazard in a sum of products circuit. Of course, in a product of sum circuit, you can have static 0, 1 glitches. But that I will leave for you to discover yourself. I think this lecture is already long enough like it is. So I hope you enjoyed it, and see you in the next lecture.